morning, everyone. Fantastic. I'm filling in for Katie Bottenhorn, who was unable to be here as well. But I'm going to dive in a little bit deeper to talk about coordinate-based meta-analysis this morning, and I'm going to compare a bit about conventional or manual meta-analysis versus large-scale automated meta-analyses. Not quite as tall as James. Here we go. Just a brief kind of roadmap of where we're going to be for the next 20 minutes is I'll give you a little bit of background and a little bit of differences between manual versus automated meta-analyses. We'll dig in a little bit deeper on each of these topics, talk about the process of how to go through these types of analyses. We'll present some examples and then some pros and cons of each of these approaches. And then we'll give you a preview of the tutorial that we'll be going through as well, which is kind of what we would like to say the best of both worlds, and that'll be a semi-automated meta-analysis process, and then we'll recap. So what I hope you gain from this talk over the next 15 to 20 minutes is I hope that you can walk away understanding the differences between a manual versus an automated coordinate-based meta-analysis. I hope you start to learn a little bit about the strengths and weaknesses of each of these approaches. Maybe think about why you might take on a manual meta-analysis versus a larger scale meta-analysis, and maybe the pros and cons of these approaches. And then finally, I hope that by the end of the talk, you might understand a little bit more about why we are going to be presenting up next a tutorial for semi-automated meta-analyses to kind of facilitate your own meta-analysis. Okay, so a few years back, Mueller et al. Put together this really fantastic paper, 10 Simple Rules for Neuroimaging Meta-Analysis. If you are not familiar with this paper already, please Google it, find it. This is kind of your best introduction in a PDF version of meta-analysis. And so one of the fantastic resources that they provide in this paper is a 8 to 10 steps of how to perform a meta-analysis. And so I just kind of want to orient you on where we are in this process of the steps that I'm going to be covering today. And so where we're going to be starting is I am assuming that you all have already determined your research question. So if it's going to be some domain, some cognitive domain of interest, some clinical population, or something similar to that, I'm assuming that you all already have your research question decided. And what we're going to be reviewing is kind of steps 2, 3, 4, which is your systematic literature review, your data extraction, and then cleaning of your data. So just a kind of high-level overview of manual versus automated meta-analyses. When you're running this manual or conventional meta-analysis, you're kind of starting from scratch. And so you are having to start at step 1. You're going through and you're using some sort of publication database like PubMed or maybe even Google Scholar to search and find all of the relevant neuroimaging papers that are related to your question of interest. And then you have to go through all of these papers and annotate all of the relevant information in them and then extract those XYZ coordinates that James was just talking about from each of these papers. On the other hand, if you're using an automated or a large-scale approach, you're starting with an existing database, something like BrainMap database or NeuroSynth, where there's already a number, hundreds if not thousands, of studies that are already populated into this database for you to start searching through. And then you can run your meta-analysis on the data that's already available within that database. So you don't need to go through and read maybe every individual paper. You don't need to extract these XYZ coordinates because they're already there. So diving into how to do a manual meta-analysis. So step 1, this image may look a little familiar from James's slides earlier. So step 1, you're going to find all of your publications of interest to your question. And so this is where you're going to be going through PubMed or Web of Science or maybe even Google Scholar to find all potential relevant studies that you're going to use for your meta-analysis. You'll then need to go through all of these papers and curate your data set that you're going to meta-analyze. And so you're going through each of these papers and you're identifying candidate studies from those search results. Once you've narrowed down into your corpus or your data set of publications that you want to meta-analyze across, then you need to dive down deeper into each of those individual papers, collect the metadata that is necessary. So that's something like, what is the sample size that each of these studies are using? What are the clinical populations? What are the subjects? Are there subject characteristics of interest for each of these studies? And so on and so forth. Maybe what are the tasks that these participants are going through, or what is the potential like GLM contrast that I'm wanting to meta-analyze across. And then you'll also need to extract the coordinates from each of those papers. So those XYZ coordinates that are actually showing you the effect that you're wanting to meta-analyze. And then finally, you'll annotate your studies for additional information relevant to your study or to your meta-analysis. So I want to give you some examples of different questions that you can ask with coordinate-based meta-analysis. So first, you can ask questions about, are there gray matter differences between different clinical populations? So here, I'm showing you Glahn et al. 2009, where they asked the question of, are there differences in gray matter between healthy controls and individuals with schizophrenia? And here you can see the red areas are showing increased gray matter volume in healthy controls. You can also ask questions about brain activity between different population groups. And so in this example that we show here, Minzenberg et al. 2009, they're still looking at schizophrenia, but instead of asking about anatomy and gray matter differences, here they're asking about differences in brain activity. So across executive functioning tasks, do healthy controls and individuals with schizophrenia show differences in brain activity? And in fact, here we see increases in activity in healthy controls compared to patients. So those are two examples of looking at clinical populations. You can go back and you can look at a very domain general. You can take a domain general approach to meta-analysis in healthy controls only. So here we have Neandam et al. 2012. And she took a very high-level approach of looking at cognitive control. So if you're familiar with cognitive control, it encompasses a number of kind of subdomains or subcognitive processes like working memory, inhibition, initiation, and so forth. And so she took all of these cognitive control or executive functioning tasks and threw them into one meta-analysis and identified a superordinate cognitive control network. She then followed up on this meta-analysis, taking a little bit of a more granular approach, and then said, okay, what if I also run a meta-analysis of working memory only? And what if I run a meta-analysis of inhibition tasks only and initiation planning tasks only? And so what they're showing here, sorry, do I have a mouse? Can you see? No, I don't. Okay. So what they're showing here in these different colors, ooh, thank you. Ask and you shall receive, thank you, is they ran individual meta-analyses of each of these tasks, and they're showing that they activate similar cortical regions. And so this is really cool because at this point it was thought that working memory and inhibition were separate networks and they engage separate parts of the brain, but in fact they are all within this superordinate cognitive control network. So you can go from a domain general approach to a more granular sub kind of level approach as well. You can then take it a step further. So Rotchke et al. In 2012 wanted to look at working memory only. And so here they threw in all of their working memory tasks in a meta-analysis. It looks very similar to that cognitive control network I just showed you. But then they took it another step further, and they asked the question of, okay, so within this working memory network, what parts of the brain are activated in just a task versus rest contrast? And so here in I think it's these red parts, is your task versus rest. So what's activated more during working memory compared to rest within this network? And then these green parts, they ask the question of which parts of the brain are responsible for the demand of working memory. So these green parts are more responsible for those areas that are a higher demand of working memory than a lower demand of working memory. So a common working memory task would be something like your in-back task. And so what we would be showing here is a contrast of something like a 3-back versus 2-back in green, whereas red would be something like a 2-back versus rest. I hope that makes sense. And then another way that you can take a similar approach and a more fine-grained approach to looking at some of these cognitive processes is following up on this working memory meta-analysis. Oh, sorry about that. Imsh et al. 2019 wanted to look specifically at verbal working memory. And so instead of looking across all working memory tasks, they honed down into just those tasks that were performed in the scanner using a verbal task. Okay, so as you can see, as James had presented, meta-analysis has been very, very successful in helping us understand more about cognition, more about brain function over the past 20 years. But there are some limitations still. So one of the largest limitations is that searching for all of these papers has low signal-to-noise ratio. So when you're doing your literature search, you're often going to get hundreds of studies from PubMed or PsycInfo. And that initial search, it's going to include a lot of studies that may or may not be human-related. They may not even be imaging studies. And so, for example, here's a Prisma table from Bottenhorn et al. 2018. When they ran their literature review, they first found 754 studies that matched their search query. And you have to go through all of those studies. And then they ended up with only 110 that really fit the eligibility, the search criteria that they wanted to meta-analyze. So low signal-to-noise ratio. As you can imagine, curating your data set, it takes time. I don't even want to know how long it took them to go through 754 studies, right? But it's very taxing and it's time consuming. Extracting those XYZ coordinates is tedious. So I spent a year as a research assistant with the BrainMap database. I have extracted coordinates from hundreds of papers at this point. It is time consuming, and I will tell you, it is prone to human error. We all make mistakes as we're keying in those XYZ coordinates. And then finally, annotation. It takes time. So once you get down to that smaller corpus of 110 papers, or however many papers you need, which James did mention, you need about 17, 18 to 24 coordinate-based meta-analysis as a bare minimum. Annotating these papers often takes time too, so you're having to go back and read through the whole paper to see and to learn more about what these studies are actually doing. Oftentimes, I like to read through these papers, and it helps with interpreting results. It also helps with writing up your discussion as you're preparing your manuscript. Okay, so why use manual methods when we have automated options? Well, the data that are already available in these large databases, like BrainMap or NeuroSense, sometimes they're insufficient for the research question that you want to ask. So on top of that, automated data extraction is noisy. Keywords included in the database might not cover the specific topic that you are interested in. And some of these large databases can't distinguish between brain activity versus brain deactivations or functional connectivity, et cetera. So here's an example of where you might want to use an automated option, but because of your research question, it's not the best approach. So we have this study by Pintos Lobos et al., where they're looking at RDoC approaches to social constructs. So their meta-analysis, it covered 239 studies, but as they're looking at differences in social constructs, they wanted to have a more granular, fine-grained approach to be able to parcelate each of their search queries into these 5 different categories of social constructs. And so this was a case where taking an automated approach would not fit their research question. Okay, so for the sake of time, I'm not going to go through this decision-making chart in depth, but I did want to give it to you as a resource for how to choose your meta-analysis method. So here we're talking about coordinate-based meta-analysis, and as James had pointed out, there's a couple of CBMA algorithms that you can use depending on the questions that you are asking. So when you're running your meta-analysis, I want you to be able to go back through and maybe run through this decision-making chart to help support that. Okay, so moving on to automated large-scale meta-analyses. What's really nice about these large-scale meta-analyses is that you don't have to do that fine-grained literature search. When you are searching for your studies, you're already starting with that meta-analytic database that's already populated hundreds, if not thousands, of neuroimaging studies. There's not a lot of curation because the data is already in there. You're not having to extract coordinates. It's already in your database. The metadata has already been extracted, that's available, and it's already there. You might add some annotations, but on the large scale side, if you're using something like 500 or 1,000 studies, it's probably the work that you put into it is probably, your ROI is not good enough. So there are 2 main platforms for automated meta-analysis. So the first is the brain map database, and this is a manually populated database of brain activation and voxel-based morphometry coordinates from published papers. I think they also have recently added a resting state database as well. An advantage of brain map is they have a very rich metadata scheme that describes the experiment context, participants, paradigms, and so on and so forth. So there's a lot of metadata that goes along with each of these studies that's in the brain map database. If you want to use it, it's at brainmap.org. There's another database, it's called the NeuroSynth database. If you can't tell, so BrainMap has about 4,300 activation studies. NeuroSynth has about 14,000 fMRI studies in the database. So you have a much larger number of studies that you can meta-analyze across. However, NeuroSynth, it's an automatically populated database. And so what they've done is they've scraped descriptive terms from the publicly available abstracts only. However, they provide you with 1,300 term-based meta-analyses already populated for you on their website, which is neurosynth.org. And these come from 150,000 plus coordinate-based co-activation maps. So a lot of the motivation for why NeuroSynth was created was to facilitate these large-scale meta-analyses approaches. It's really not feasible with manual curation methods, as I had outlined before. And the way that they work is that as you are scraping the text from the abstracts, you're getting this term-based search and a term-based approach. And they're able to link these terms with the XYZ coordinates in the studies. And then they perform a meta-analysis based on probability activation of your term of interest across a null model of all of the other studies in the database. NeuroSynth has been extremely successful over the past 10 to 15 years. Sorry about that. But again, there are some limitations with every approach that you have. So for example, in NeuroSynth, if you wanted to look at a large-scale meta-analysis of pain, you would have to take a very high-level general approach to looking at pain, and it doesn't allow you to differentiate between topics like emotional pain versus physical pain. So that is kind of a drawback. But in comes NeuroQuery, which is another resource or another platform for automated meta-analysis. And so it's a newer database, similar to NeuroSynth. It's automatically populated with brain activation coordinates. But in this case, this provides you with predictive modeling results. And so in this case, with NeuroSynth, you could predictively model differences between different types of pain. So what I'm showing you here is an example of a predictive model for pain perception. And then here's your predictive map versus emotional pain and the predictive map. You can see that there are some similarities, but there are some differences between the two different predictions, the different types of pain. So a couple of examples of automated coordinate-based meta-analyses. First up is Smith et al. 2009. So they ran an ICA analysis of all of the images in the brain map database. And they also ran a comparable resting state ICA analysis. And they found that about 2/3 of these ICA components matched up between the task-based meta-analytic networks and the resting state networks. Following this study, Laird et al. 2011 then took those brain map task co-activation networks and was able to access all of the rich metadata within the brain map database, and they were able to provide cognitive profiles, so behavioral profiles for each of those networks, and then they were also able to cluster each of these networks based on their functional profiles and determine groupings of these intrinsic co-activation networks. A very different approach is Chang et al. In 2013. They were looking at the insula, and they used co-activation-based mapping approaches to parcellate the insula into 3 clusters. And then they found that those 3 clusters had 3 different co-activation maps, as you can see here. Then they used functional decoding to then provide the corresponding behavioral analysis or behavioral descriptions of each of these insular co-activation maps. And then finally, Han et al. 2021 was able to use meta-analytic maps to create a priori distributions for Bayesian analyses of fMRI GLM analyses. Okay, so when should you use automated meta-analysis approaches? When you're wanting to take a more general, domain general or co-activation-based approach. When you're wanting to look at meta-analysis, mostly for hypothesis generation. So in this example, you could use large-scale meta-analysis for making ROIs to then seed for your primary or raw data, potentially, connectivity studies or any other type of studies. You could also use it for selecting brain regions for some sort of stimulation study later on, or here we have an example of spectroscopy. Automated meta-analyses also allow you to do functional encoding as well as functional decoding. And thank you, Kendra, for these slides. What are the limitations? So large-scale meta-analysis, it seems great and very well-powered, but neither approach is perfect, right? So here, searching is limited. You're constrained to your database. There's less flexible curation because the data is already in there and you're not able to select studies as easily. Extraction can be noisy, so not all of these databases differentiate between activations, deactivations, and annotation is hit and miss. Okay, trying to run through this quickly, sorry. Semi-automated meta-analyses, so we would like to think that this is the best of both worlds. So what you're going to hear about next is going to be NeuroSynth Compose, where the goal is to make searching for studies easy. Curation will be facilitated using Prisma workflows. Extraction is mostly done, so this is based on NeuroSynth, where they've already extracted the coordinates for you. on many, many papers, and they facilitate using an online platform, annotating and sharing your the studies in your data set. So Neurosynth Compose, if we compare Neurosynth to Neurosynth Compose, they are both based on a similar database. They both have a browser workflow. And new tools or new capabilities is that they enable editable study sets, filterable studies as well. They also support multiple meta-analyses, CBMA algorithms. Sorry about that. And then they're working on, and I don't know if it's already in there, but the plan is to also incorporate image-based meta-analysis as well. One thing that's really cool is they have already populated a number of meta-analyses in Neurosynth Compose for you to kind of use as examples and to work through and learn from. Thanks, James, for putting all of that together for us. So recapping, last slide, almost done. So hopefully you understand a little bit more about the differences between manual versus automated meta-analysis. Hopefully you're excited to learn a little bit more about semi-automated meta-analysis and how it's the best of both worlds to reduce all of the time-consuming constraints in a manual meta-analysis, but also benefit from the automated approaches as well. And then share your maps, because as we mentioned, image-based meta-analysis is a more robust approach, but the drawback is that we're not sharing our images, our maps, enough. So thank you all, and on to the next if you don't have questions.